Hi students, and we are back and we are going to do our Pset 1 solutions for spring 2022, excuse me, for our materials tetrahedron for ENGR045. So let's go ahead and read the first question. So we want to read the following article on spider silk and analyze the article filling out our materials tetrahedron, which is composed of, basically, we can kind of draw it going back here, here, here. So we've got at each of these four corners, we've got structure, we've got properties, we've got performance, and we've got process. So what's going to happen here? So we want to read our article, and let's go to our spider silk article. And you see that spider silk has this kind of unique fibril structure, very similar to Kevlar. So this unique kind of aligned fibril structure gives rise, so the structure, which is fibril, gives rise to these intermolecular interactions, which changes essentially the properties of the fiber, making it extremely stiff. Stiff and also having a high yield strength. So excellent mechanical properties, and thus performance mechanically. So this fibril structure and these intermolecular interactions affect the properties, especially the mechanical properties, and thus the performance of our material. And the process that we can use is you can process spider silk to make it even more aligned. Again, very similar to Kevlar like we discussed in class. So that's what we're looking for on problem 1. Now, classify whether the statements are true or false, and if false, correct the statement. So remember, if false, correct. So covalent bonding can reform at room temperature. No, that is false. Why? Because it is greater than 1 kT energy. H bonds have an energy greater than 1 kT. No, they are intermolecular interactions. So intermolecular, and thus less than 1 kT. Those interactions can break and reform at room temperature. Destructive interference leads to no signal on the intensity versus 2 theta curve. True, but to be very precise, perfect. Perfect destructive interference leads to no signal. All right, to measure atomic distances, I need to use a wavelength much, much less than 1 angstrom. Well, that's not true. Remember, we said that what we need is a regularly spaced array of obstacles, right? And then we needed a lambda wavelength that's on the order of the distance with these particles. So in atomic structures, you're dealing with, distances on the order of an angstrom. So that would actually work just fine. So you don't need much, much less. Actually, we want it on the order of. If it's too small, we can't investigate these other higher order structures or long-range interactions. Bragg derived his equation by realizing that destructive interference between waves has a mathematical relationship. No, constructive. And then the extra distance that the waves travels via Bragg angle must be an integer number of wavelengths in order to achieve, again, not destructive, constructive interference. And that's number 2. Classify whether these statements are true or false, and if false, correct. Okay, so another one of these. Covalent bonds are intermolecular interactions with an energy of 200 kT. This value can fluctuate, but the key thing here is this is intra. Intramolecular interactions can break and reform at room temperature. Again, no, this must be inter. That's the truth. Metallic bonds gain or lose electrons. No, they are delocalized. Ionic bonds will gain or lose electrons. Covalent bonds share electrons. Oxygen is a cation. Nope, it is anion with -2 charge. H bonds and van der Waals interactions are intramolecular interactions. Nope, again, inter. We did a lot of intra and inter in this Pset. What type of bonding will be exhibited by, vanadium? Vanadium is a metal, so therefore that will be metallic bonding. That cannot be, that cannot break and reform at room temperature. Instead, those electrons will be delocalized. Let's do MgCl2. So here we need to look at our old friend, the periodic table, and we could pull up Mathematica. Cl is 3.16, I remember. Because here we need to distinguish, is it covalent or ionic, and then we do that based on electronegativity differences. Come on, Mathematica, open up. There you go. Sometimes in the morning, it takes a little bit of coaxing to get Mathematica up and running, but no fear, we will be able to do so. So no worries. All right, so we got Cl is equal to 3.16. Let's look at, and I'm going to look at oxygen as 3.44 for electronegativity differences. Because you can see that right here. So this is for oxygen 3.44. And let's look for magnesium, our good old friend. Magnesium is, oops, let me erase that here, 1.31 for electronegativity. So let's look at Mg. Then I think we need U, uranium. Let's look for U. U02. U, here we go. U is 1.7 here. And then let's try to get back to what is our problem set asking us to do. All right, fantastic. So let's go ahead. We'll take the difference. So for Mg and Cl, Cl minus Mg, yeah, that's going to be ionic. U, or actually O minus U. That will also just be ionic because, again, 1.7 is our threshold for this class. So again, those are all ionic. Those will basically grab and steal electrons, and those will not reform at room temperature. For PET, polyethylene terephthalate, that is a polymer. So as you can see here in this structure, the polymer will have covalent bonds in these CC bonds here. But you also have these oxygens here that could potentially participate in H bonding. They're polar interactions, so you could have these kind of slightly polar dipole-dipole interactions. This huge phenyl group will also give you steric interactions and van der Waals as well. So you've got lots of intramolecular, or we have one intramolecular covalent, and then lots of intramolecular interactions that can be happening here. And those intramolecular interactions can break and reform at room temperature. Great. Mg, Cl2, Mg is our cation, 2 plus, Cl minus 1. So again, losing electrons, Cl will gain electron, Mg will lose 2 electrons. Ta2O5, Ta is 5 plus, O is 2 minus. O is always 2 minus. So again, we see we have 5 oxygens, so 5 times 2 is minus 10, and then I need 2 Tas because that's plus 5. And Fe2O3, Fe is 3 plus, O is 2 minus. Same thing, 2 minus times 3, minus 6, 3 plus times 2 is plus 6. Excellent. Now, very, very fun problem with basically van der Waals, or Leonard-Jones potential. So I'm going to look now at Leonard-Jones potential. So we know we're given essentially here that epsilon equals 0.25 EV, and I'm going to multiply that right now because I want to work in joules. 1.61 times 10 to the minus 19. Actually, 1.6. Anyways, it'll approximate that. I get it sigma equals 3.63 times 10 to the minus 10. And now I could do that my Lj is equal to 4 times epsilon times sigma divided by r to the 12th minus sigma divided by r to the 6th. So this is my Leonard-Jones expression with these values plugged in. So I'm going to do, I want to find equilibrium distance. So equilibrium distance is just going to be simply the derivative. I'm going to solve where does this function minimized or maximized. Take the derivative of Leonard-Jones with respect to r, set it equal to 0, solve for r, and give me the, solve for r, give me the reals. And this is my distance. So in vanadium, I could double check, is that my equilibrium distance? That distance is equal to 2r. So I could check, again, on my periodic table. I could look at the atomic radii. Let's get out of here. Or I could look at the metallic radii. Since it's the metal. We could look at the metallic radii, which is the second one down. Let's look at vanadium, which is on the next page. So if I look at vanadium, 1.36, so 1.36 times 2. So something is off there. So Wan's results need to be a little bit You need to double check a little bit. So something's off there, but let's continue with what the problem's asking us to do. So we found our equilibrium distance. We know that the force is equal to minus derivative of LJR, and then I need to figure out where the force is maximized. And then so that's going to be solve derivative force with respect to R set equal to 0. R, give me reals. So I have that distance there, which should make sense when we get back to looking at our values. And we want to see what's the value of force. R goes to 2 times 10 to the minus 10. And that's going to be force value in newtons. So we can figure out where all of those are, on our Leonard-Jones potential. We know that our basically equilibrium distance, REQ, equals 2R, which is right here. We know that force is maximized because that's the second derivative effectively. So that will be the inflection point here. And then we know that atoms will attract here and they will repel here. Excellent. Finally, isomers, conformers, neither. These stereoisomers, iso, syndio, atactic. If we look here, remember isomers are conformers and isomers, they need to be chemically identical. So here there's a bunch of H's and Cl's, but I see some F's, so neither. And then here I have 2 Cl's, I have 3 Cl's here, so neither. That's it. So that is problem set 1 done. So start on problem set 2, and I will see you all next time. Thanks. Bye.